Hello, everybody. Welcome to the Atto Fridays. Our speaker today is Professor Adriana Pálwiąy. We have known each other for a long time and actually were complaining about conferences, but I'm really happy and honored that she accepted to give this talk. She is a theory professor at the University of Würzburg in Germany. And by understanding light-matter interaction and the borderline between atomic, nuclear, and quantum physics, she aims at obtaining quantum control over nuclear transitions. So this is something, although she told me, okay, give a disclaimer, I'm not an Atto scientist. We know, but we are really happy to have you here today because this is a piece of information that is very important for our field at the moment. Adriana studied physics in Bucharest, Romania, and received her PhD in theoretical physics at the Justus Liebig University in Gießen, Germany in 2006. She later moved to the Max Planck Institute for Nuclear Physics in Heidelberg and became a group leader in 2011. And in 2019, she was awarded the Hertha Sponer Prize of the German Physical Society and the Röntgen Prize at University of Gießen for her work on X-ray quantum optics. Since 2020, she is a Heisenberg Fellow of the German Research Foundation, first at the Friedrich Alexander University of Erlangen-Nuremberg, and since April 2022 in Würzburg. And today she will talk about X-ray quantum control. So we're happy to have her here. Please feel free to start. The floor is yours.
Thank you very much. So full screen or pseudo full screen. It is now, right? And you can hear me and you can see the slides. Yes? Okay, Carla was already. Thank you so much. I'd like to start by telling you how happy I am that I was invited for the Atto Fridays, although I have nothing to do with Atto physics. You'll see that the processes we are investigating are running on completely different time scales. Nevertheless, it's about X-rays and about quantum control. And the incentives that we have for controlling X-ray quanta, so X-ray photons, are that compared to visible light, X-rays are very robust. They can be very efficiently detected, and they also penetrate very well through material. They can also be focused much better than optical photons, right? So we are typically limited by diffraction when focusing. And if you're taking optical light, then you are limited to the optical wavelengths, right? A few hundred nanometers. Whereas with X-rays, in principle, if you think of an atom matrix illuminated by light, if you take an optical photo focus, you always have many atoms inside the focus, but if you have X-rays, potentially you could really go to illuminating a single atom at a time. Now, this would mean that we are in front of an ultimate miniaturization possibility for instance, photonic circuits, also for sensing with unprecedented spatial resolution. So these photons are special and are cool through their properties. And what we also have, when we have had for the past maybe 15 years, is that we have very intense sources of X-rays, right? So we have the first X-ray lasers, and I'm talking here about the X-ray free electron lasers. The first one, which started operation in 2009, was the LCLS at Stanford, so linear coherent line source. 2 years later, in 2011, SAKLA in Japan started, and by now we already have in Germany, in Hamburg, the European X-ray free electron laser, which has now light at the end of the tunnel, as they announced it, I think since 2016. And first beam times have been already scheduled and performed. So we have these sources and we have this incentive for X-rays. And the vision would be, if we would be able right now to take these sources and build for them so-called photonic devices, so components that can manipulate light. And now the light would no longer be visible light, so maybe we should not call it light, right? These would be X-ray radiation, so that we can have X-ray control with unprecedented spatial and energy resolution. So I think here the accent is more on the frequency of these photons, right, and not on the fact that things happen fast. In our case, things do not happen fast. You'll see, especially using nuclear transitions, we are very far from the attosecond regime. And the idea would be at the end that if we are able to design some devices, right, then you would come with a strong X-ray source. This could be some plasma-based source, which is kind of tabletop if you want, like a larger table, but still somewhere in your lab. Or you could have these large facilities like the X-ray free electron laser. And then you would have in front of the beam this photonic device, which selects few X-ray photons and then controls the propagation, maybe switches them from one direction to the other, stops them, releases them, manipulates some of the properties, for instance, phase. So if we would have such devices, then we could go in towards many applications, either in the direction of quantum technologies, where we could have, for instance, quantum imaging or X-ray qubits. We could go towards designing new types of sources like X-ray nanolasers, or we could go more towards material science or biochemistry, exploiting exactly these wonderful properties of X-rays, that they have such small wavelength and they can basically visualize at very small dimensions. So all this could profit from having such devices which control X-ray quanta. And now, allegedly, this might be challenging. And if we just make a one-to-one comparison between the X-ray realm and the optical transitions that we have, and we know, right, typically, if we're talking about optical light, we use resonant transitions to control this optical radiation. And these are typically, if you're looking at electrons, simply valence electrons, so electrons further away from the nucleus, which have transitions in the region of maybe 1 electron volt. Well, X-rays have 10,000 electron volts, so they are no longer resonant to atomic valence electron transitions. They are rather resonant to transitions between the outer shells and the core shells, right? Maybe the K shell in the atom. And well, for that, in principle, you need to have vacancies there, so it's not that trivial anymore, right? So we need different types of electronic transitions or different types of transitions, period, to have resonant transitions that allow you to control light. Now, the other drawback that we have is that for the moment, the sources that we have, the X-ray sources, do not have the same temporal coherence, good temporal coherence that optical sources have. So the X-ray free electron laser definitely lacks the coherence properties of optical lasers, especially in longitudinal coherence or temporal coherence. And another problem is that a lot of very cool stuff that we've done with quantum effects for optical light was based on cavities, right? If we are thinking of the high reflectivity cavities that are used in the group, for instance, of Serge Haroche, who got the Nobel Prize for that, right? So that's the place where you get a single atom interacting with a single photon and many interesting regimes and effects. But those cavities, for the moment, we don't have. So we are lacking for X-rays, high finesse X-ray cavities, which would allow you to enhance basically the light-matter interaction for this frequency range. So this is, so to say, at the moment, the incentives, but also the challenges for this. And what I will tell you about today is some developments in the field of X-ray quantum optics, where we are using now, instead of atomic transitions, nuclear transitions, which are resonant to X-ray photons, in order to control somehow these X-ray photons. So for this, I need to remind you, because this is the most silly question that I can get at the end, is that when I realized people did not get the point that these transitions are inside the nucleus, right? So in atoms, it's clear that you have these electrons and you can shift them up and down, right, with light, and they decay back. So these would be jumps, if you want, between atomic shells. But the nuclei, they also have states, right, the ground state and excited states, and you can also have transitions basically inside the nucleus. They are electromagnetic transitions inside the nucleus. And these are the transitions we're talking about, because they are rather resonant to X-ray radiation. And the workhorse that we use is typically the Mörs nucleus iron 57. So it's an iron nucleus which has 57 nucleons in it. It's stable and it has the ground state, inside the nucleus. And the first excited state of the nucleus is at 14.4 keV, kilo electron volt, and that's the equivalent of about 1 angstrom wavelength of an X-ray. No? And now what we do is that we put these nuclei in a specific environment, and the specific environment we call thin film cavities, although you'll find out the cavities are actually very lousy, so it's not a good cavity, it's a very lousy cavity, but okay, let's put it this way. It's a nanostructure, so imagine here, this thing here is a sandwich. We have a sandwich with very thin layers. Each of the layers that you see here is about nanometer thick. So in total, you're going to have maybe 20, 50, a bit more than 50 nanometers. And what you do is that you start with a high Z material, so a material with high atomic number Z. And then you have some lower Z material where this is used basically as a buffer to position the layer that you're interested in, the green layer here, at the proper position inside the cavity. And then further on, you have again this buffer layer and again a high Z material. And you come with the X-ray pulse in grazing incidence. Grazing incidence means that you come at a very, very small shallow angle. And then typically light couples here evanescently, and there is a standing wave forming in this direction in the cavity. And this is depicted here on the right-hand side. What you see is in color, the intensity of light. So coming at a specific angle, you're going to have a big light blob, so to say, forming as a standing wave inside the cavity. And now you want to position these nuclei, the nuclear layer, so the iron layer, at exact position somewhere in this standing wave. And what you'll see is that actually you have here very strong collective effects. So all the nuclei see this field at basically the same phase, and they behave as one. And these collective effects bring us means of control. So this is basically, in a nutshell, the type of setup that we will investigate. We will investigate how X-ray couple in these nanostructures to a material which has a resonant nuclear transition, which is resonant to that X-ray pulse. Okay, so that's more or less the nutshell of the introduction. And I'll have two parts. The first parts will tell you more about the physics inside the X-ray thin film cavities, and I'll give you a few neat examples of what we have been investigating. And the second part is what are we working on right now. So this is more of the unpublished stuff and the wild ideas that we are pursuing and what we plan to do. Okay. Now, as for the first part, I'll tell you a few more details about these thin film cavities first. So again, sandwich of several layers, each of them few nanometers thick. The green layer is the one that is interesting for us, and the green layer we want to position at the proper place, so to say, in the cavity field. And you see again this intensity of the field inside the cavity. The white stripes depict where the positions of the layers are. And here down, for a better understanding, I've plotted the reflectivity here at the detector as a function of the incidence angle, right? So the angles are very small. You see, we're talking here about from 1 to 6 millirad. And you see you have this minima. Every time you have a minima here in the reflectivity, it means that the light did not reach the detector. It means that the light stayed here. And this is exactly the moment when that standing wave builds up. And the standing wave has different patterns depending on whether you're on the first minimum, then you have just one blob. If you're on the second minimum, you're going to have two blobs. If you're on the third minimum, you're going to have three blobs, right? So it depends exactly on which angle you come to see how exactly the field looks like. And the nuclear resonances, so that those nuclear transitions, which are resonant to the X-rays coming in, they interact now with the cavity field. And just to show you a real life picture, the real life picture is that the entire setup here, so these few tens of nanometers, are this polished surface that you see over here. So this is a sample, but actually most of it, so what you see with your bare eye is the silicon substrate, and on top this glittery surface, that's where the 50 nanometers of interest are. Yeah, and your X-rays come here through the tube and then just go here further towards the detector. And this is a setup at DSZ Hamburg, at the synchrotron this time, not at the X-ray free electron laser. Okay, Now, let me tell you why we like so much these types of cavities. Well, we like them because they allow us to have very strong collective effects, namely very strong superradiance. Maybe you've heard of this term before, maybe you haven't. I will give you directly an example, a real life example. There's some measured spectrum. All right, so what you see here is the intensity of the scattered photons at the detector as a function of the time after excitation. And for the attosecond people among you, I expect most of you, you will see here nanoseconds. So this is probably very, very, very slow for you. Yeah, but this is how it works. The nuclear resonance we are working with has a half-life of 141 nanoseconds. So, okay, now, so what you do, you come in here with your X-ray pulse, you're looking at the detector, what's going on, and you have always, since the pulse comes in the synchrotron at a certain moment, you are measuring the time after the pulse has been coming. And after some time, you get the response. So typically the electronic response from the sample, there will be some electronic response. This would be instantaneous if you want, so much shorter time scales. The pulse itself at the synchrotron is about 50 picoseconds. And the nuclear response comes much later. So you can basically see it as a delayed response. And by time gauging, you can simply cut out the pulse, which comes and hits the detector at t equals 0. And also the electronic response, which hits the detector at t equals 0 plus much shorter times than nanoseconds. So much later, you'll see what comes from the nucleus. And typically, these synchrotron radiation pulses, they are rather broad compared to the nuclear resonance. The nuclear resonances are, fortunately or unfortunately, very narrow. We're talking here about nano electron volt. So basically, this leads to the fact that an X-ray synchrotron pulse typically has just one resonant photon to the nuclear transition. So you're going to see per pulse basically at most one photon coming out delayed, coming from being scattered by the nuclei. And still doing this because you have a high rep rate at the synchrotron, you have megahertz rep rate, you will see at the end you get many counts. Yeah, you see here going up to 10 to the 5th. And these counts will here come on a straight line. This is a log plot, so we are talking about an exponential decay. And now the interesting thing is, if I'm looking at the table and I know what is the lifetime of iron of a single nucleus, basically the incoherent spontaneous decay, then that would give me such a line. So see, actually the response of a single nucleus would be a much slower process. But what you see here is a much faster process. And this has to do with the fact that the nuclei behave collectively, right? So the cavity field basically excites the radiative eigenmode of the system. And this radiative eigenmode decays much faster. And this is what we call the superradiant decay, right? So it's super radiance. And this means the collective effects are very strong for us because, say, a single nucleus would decay this way, but the collective part of it, the fact that they are all together and they see the cavity field at the same phase, allows them to decay much faster. And what you see here, the tail is basically the admixture of some hyperfine splitting that we had in the sample and we could not avoid. But basically, the nice thing is to compare these two straight lines. And the interesting part is that these collective effects are for us the control knob of the system. So we can switch them on and off. But before doing that, I'll just give you a short tutorial on the topic of superradiance to understand how this happens. So if we're thinking of the spontaneous decay of a single atom, what we know is that the classical field description would not explain it, right? So we definitely need to introduce a quantized field description, which tells us that in principle our field level system that we have here, be it an atom or be it a nucleus in our case, interacts now with the vacuum, and there is an infinity of vacuum modes, right? There's no photon in them, but the modes exist. And well, you know, we tend to have things simple, so we'll remove all other levels and say we have just a two-level system, like in our case, nuclear ground state, nuclear excited state. Later on, we will put in these vacuum modes, which are depicted here by these wiggly lines. And once we introduce this vacuum modes, then we'll see in our theoretical treatment that yes, we have some decay, and this is a spontaneous decay, and we know that it's basically it's proportional to the dipole moment and also to the density of modes basically in the vacuum. Now the question is here, let us take several such atoms, all identical and all interacting with the same vacuum. And the question is it possible that these many identical atoms interacting with the same vacuum may be decayed differently? And the answer is yes, right? And this is where superradiance comes from. So this is the picture you should have, right? So instead of having all vacuum modes interacting with a single two-level system, I'm going to have all these vacuum modes, the same vacuum modes interacting with many identical atoms or two-level systems, in our case, nuclei. And the basis for this was established many years ago by the Dickey model, by Robert Dickey, and he is also the one who coined this term, superradiance. In the paper, it's written that for want of a better term, a gas which is radiating strongly because of coherence will be called superradiant. Yeah. So imagine now we have all these n two-level systems, and they are all close together. What is important? Well, it is important that when I excite them, or when they decay, that the wavelength of this radiation is actually much larger than the interatomic distance, or the distance between each of these two atomic or identical scatterers, whatever they are, atoms, nuclei, or whatnot. And that's important. So we would need that the wavelength of radiation is much larger than this interatomic distance. And in that case, right, if all these atoms see the field at the same phase, then one could expect the superradiant decay increased by a factor n in the exponential. And that's, of course, very strong. This is to a certain extent what we've seen in these thin film cavities, because until the decay was exponential, it was much steeper than the one of a single atom, which would be this gamma, right, the spontaneous decay of a single atom. And in theory, Dickey put off his model in 1954. An experiment, the first experiment noticing and observing superradiance was almost 20 years later. Now, if we're thinking of how do we explain this in formulas, right? Okay, if we take just two atoms, then it's pretty simple, because with two atoms, what we will see is that, okay, we take two atoms, we have a total dipole moment operator, D1 plus D2, and this is invariant to transposition of atoms. And this leads to the fact that in principle, you can build up a symmetric and an antisymmetric state, right, with the excitation being in the first atom or the second atom. And because the total dipole moment operator is invariant to transposition of atoms, it turns out that actually a state with a double excitation will not decay via the antisymmetric state at all, but will decay just via the symmetric state, and it will decay with twice the decay rate of a single atom. So this is where basically this n comes into play. But of course, if you go with more than two, then things will get more and more complicated, right? Because you're going to have many possible combinations of symmetric, antisymmetric, partially symmetric states, whatnot. So it's not that simple. Nevertheless, we can think of exciting an ensemble, for instance, with a single photon, and writing down what states we can have. So if I'm sending in a photon, I have like here 5 identical scatterers, and then I see what's going on at the detector. Actually, I will have interferences between all possible decay pathways, which are like one of the atoms has been excited or any of the other atoms has been excited. So each of the intermediate states will all decay to the same ground state back. And this is leading us to the so-called decay state, which is this superposition of states with a single excitation and all other atoms in a ground state. And it's normalized by this factor 1 over square root of n. And this state indeed has an n times faster decay. Such a state I can only expect to have indeed if the wavelength of radiation is larger than the interatomic distance, because in case this is not, I will have, for an expanded sample, some phases, right? Where here I have basically the position of each of these guys. And if the wavelength is much smaller than the interatomic distance, then I would be I could be in trouble because of this phase. So this phase could ruin, so to say, the fact that you want to get superradiance. So the resolution here is that if you have an extended sample, which is often the case in experiment, and it's our case as well, it turns out that if it's possible somehow to prepare this symmetric state, which is decaying faster, and which we can call the radiative eigenmode, via some geometry or some couplings, then it's possible indeed to obtain superradiance. And this is what we see in our thin film cavities. So at the end, if you're looking at the temporal dynamics of the radiative eigenmode, you see that you have here an addition to the spontaneous decay rate, and this will be the superradiant decay rate, and it could be much larger than the original gamma. And interestingly, there is also some shift of the transition frequency, which we call collective length shift. And in principle, this is what has been observed in this experiment. I've shown you so far this plot, which is the superradiant decay, and this is very clear, right? Instead of having a straight line in log scale here, you have the straight lines down. Why do you have two? I forgot to mention is because you had two different samples. So there was a sample with two different thicknesses, and for each of the samples, you get a different superradiance factor. And also what has been in the same experiment, I could also see this shift which appears in the frequency, the so-called collective length shift. And now what's important for us is that we can find means of controlling the superradiant decay. For instance, by switching it on and off, we can, with magnetic fields, you can simply destroy the strongest decay channel in the system. And that's kind of very, very important, right? So that gives you interesting applications. And these are the few applications that I would like to show you that we were working on from theory side. For instance, what I've mentioned is magnetic field. So it turns out that if you start with, light comes in where you have a magnetic field on, then there is some hyperfine splitting of the ground state of the nuclear transition and the excited state of the nuclear transition. And it turns out that, you can leave the pulse coming in while the magnetic field is on. And if you can switch off the magnetic field while you are still waiting for the nuclear response, so basically in the time between t equals 0 and t equals a few nanoseconds when you see a response, then you can stop, so to say, the excitation and store the X-ray pulse inside of your sample. When you switch on the magnetic field back on, then the pulse will disappear. And the plots I have here are from this second paper, which show you basically the electric field as a function of position and of time for such an evolution of the magnetic field where you have magnetic field at the beginning, and there is after some time a switching off of magnetic field, and you switch it back on. And you see that actually during that time, the field has disappeared. It's basically stored in coherences inside the sample. And once you switch on back the magnetic field, then the field comes out. So basically the pulse has been stopped, and then it continues once you have again the magnetic field. And this is based basically on the fact that you are switching on and off actually the superradiant part. The superradiant part is the strongest channel, decay channel of the system. So that's kind of a neat example. Another example that I'd like to share with you is what we call mimical strong coupling. And we interpret this like a kind of ping pong. So if you're playing ping pong, then or table tennis, you'd like to have a nice game. So you'd like, in principle, to exchange the ball many times between the two players before eventually somebody makes a mistake and then the ball is leaving. And in our setup, we could design basically a setup where we are having a ball, which is the X-ray photon. And this successful game means that we could have an exchange, a controlled exchange of this photon many times before we lose it. And this can be mimicked as the strong coupling regime. Let me explain a few more words so that you understand what I'm talking about. For this setup, we need not just one iron layer, but two. So we have now two green layers in our cavity. Otherwise, it's the same story. So we have our sandwich of layers. There are two of interest right now. we are coming with the X-ray pulse in grazing incidence. We are checking at the detector what's going on. And what we also know is that these experiments were done at the synchrotron, where we know that typically at most we have one resonant photon. So we are talking per pulse on about one single X-ray photon, which is coming in, and it's exciting either basically the collectively the layer number 1 of iron immersed bound nuclei, or the layer number 2. Now, each of these layers has a decay rate, so we could lose, so to say, to the environment that photon. What we also have is, because of the cavity field, there is here a coupling between the two layers. So we have now basically the situation of ping pong. We have the resonant X-ray photon is our ball, and the two rackets are excitation in the first layer or excitation in the second layer. Each of these layers could lose the ball. This would be our decay rates, gamma 1 and gamma 2. And we have also this coupling introduced by the cavity field. So you could see it also in a simple quantum optics picture. You could have the excitation in layer 1, you could have excitation in layer 2. You can have the ground state, meaning that the photon has been lost. And you're reaching with rate gamma 1, this ground state from having an excitation layer 1, or with gamma 2, rate gamma 2, the ground state after having an excitation in the layer 2. And we have this coupling. Now, in cavity QED, we call strong coupling that situation when a photon is exchanged between the atom and the cavity field many times before it is lost. Now, that would be strong coupling. In our case, we are interested in a situation in which this coupling between the two excitations, layer 1 or layer 2, is stronger than the losses, which would be gamma 1 or gamma 2. So here, basically, it's not the exchange between the photon field and the nuclei, but it's the exchange between excitation layer 1 and excitation layer 2. So it's not exactly strong coupling. That's why we call it like mimicking strong coupling, if you want. But the physics is very similar. Now, it turns out that all these three rates, the omega, gamma 1 and gamma 2, they all depend on the incidence angle of the X-ray pulse. So if we're looking now at these rates as a function of incidence angle, it turns out that the blue rate, which is the omega, the interlayer coupling, is indeed in some regions much larger than the decay rates. And this is where the experiment has been performed. And this is where we reach this regime of mimic stroke coupling. What do we have typically with stroke coupling? What we know from cavity QED is that you see a splitting of the resonance. And the splitting of the resonance in energy, which we call vacuum splitting, is translated in the time domain into an oscillation, which is called Rabi oscillation, right? And this is exactly what has been observed in the experiment, because this cavity has been indeed fabricated, has been placed in the beam, and spectra have been taken at various angles. And indeed, we have found the angle for which you see here a split of the line. Here should have been a single line normally, but you see the split. And in the time domain, you see the Rabi oscillation. So these were, so to say, the signatures that indeed we could basically play successfully this ping pong by having that photon being exchanged many times between the two layers before we've lost it, or like respectively, we've seen it at the detector. And we were very happy, but that this setup made it on the cover of Nature Photonics at the time, because it's a good advertisement for our field, which is a small field, right? So it's not everybody doing X-ray quantum optics. Okay, now this is already a long time ago. And what have we been doing in between? Well, in between, we have been tackling the hardcore theory, so to say, because so far it was difficult to find a quantum model like in cavity QED to describe these cavities, because they are far more complicated than a regular optical cavity. And on the other hand, there are some other semi-classical methods which describe well the spectra, but where you have absolutely no understanding of what's quantum in it. So they just work with classical fields. This is why we tried to find something else, and we were developing in the past few years a green function formalism that is very versatile that is in principle fully quantum because it uses a quantized electromagnetic field and quantum fluctuations. And it allows us now to treat these cavities in many ways. So both in grazing incidents, what I've talking about, I've been showing you, or also coming in front coupling, so coming from the side, where basically you have some translation invariance is lost because you really see a kind of waveguide propagation type of geometry. And right now we have a very strong tool which gives us access to the quantum part, so to say, of this X-ray scattering for any complicated structure. For instance, I present to you here a spectrum of the reflectance as a function of incidence angle and detuning for a cavity which has 30 layers, right? So not just 2 iron layers, but 30 iron layers. We have basically now this tool with which we can play and do whatever we want. Now, at this point, whatever we want, things are right now in progress. So this is why I'm going towards the current wild ideas. So I'll tell you about 3 things that we are working on right now, applying these formulas that we have been developing. And the first wild idea that I would like to discuss with you is starting from non-Hermitian photonics. So non-Hermitian, right? Sounds not much like quantum mechanics, because in quantum mechanics, so far we know we always use Hermitian operators. Now, in mathematical physics, some decades ago, some people came with interesting ideas. Namely, they've noticed that you can take a non-Hermitian Hamiltonian. If it is parity time symmetric, then it will have real eigenstates. So this basically mimics, so to say, what we know from Hermitian operators, because Hermitian operators have real eigenstates, and this is where we are getting our observables from, right? We have these conditions in the postulates of quantum mechanics. We want to have Hermitian operators that give us then the observables, which are the eigenstates of these operators, and they have to be real because what we measure is real. Now, it turns out we can have this also for non-Hermitian Hamiltonians, which obey parity time symmetry. Well, this is mathematical physics, right? Quite abstract. Nevertheless, a few years back, people have realized that actually this could have some practical implications, because the Schrödinger equation for complex potential, from which we get the non-hermiticity of the Hamiltonian, is actually equivalent to the electromagnetic wave propagation using a complex optical potential. And then applying the same condition of parity time symmetry, it turns out that there is a kind of, it's a trick that you can balance gain and loss in your beam propagation. And then very interesting propagation effects appear and control possibilities for your beam. So this was kind of a very interesting development towards extending photonics now to the entire 4-dimensional space of complex optical potentials, meaning complex permittivities and complex permeabilities. And this gave new functionalities like lasing or beam propagation, secondary emission, topological features, and whatnot. So it was really something very unexpected and something really very practical in photonics, optical beams. Now we are interested in X-rays. And what it occurred was when our cavities that we've been discussing is that, okay, actually it's interesting. If we're having magnetic field, I told the magnetic field would simply split the nuclear ground state and the nuclear excited state according to their spins. And we are taking specific beam polarization and beam geometry such that we are driving now just the 2 delta m equal to 0 transitions due to selection rules. Well, it turns out that actually the Hamiltonian that we can write, which includes the cavity loss that we have, looks very much like a PT symmetric or PT non-symmetric non-Hermitian Hamiltonian. Namely, depending on the value of the magnetic field, one can be in the PT Broken's phase or in the PT symmetric phase. And it's something that we plot here. So these are the eigenvalues of this non-Hermitian Hamiltonian. And you see something very interesting, namely in the real part, you see that for up to specific magnetic field, actually these eigenvalues are having a zero real part and two different imaginary parts, and they come together at a specific point in magnetic field values, starting from which there are two real parts which are different and one imaginary part. Now, the perfect story would be if this imaginary part would be here at zero, which is not. You see that actually after this 4 Tesla magnetic field, for larger magnetic fields, you have a constant imaginary part. And that's what people call typically quasi-PT. So there is an overall loss. But the interesting part, which remains and is very similar to what we see in optical photonics, is this kind of coalescence of eigenvalues at this particular point. This point is called exceptional point. And what we know from optical photonics is that at the exceptional point, the system is very sensitive to external control. And this can give you basically at the spatial interface between a PT broken phase and a PT symmetric phase, some additional means of controlling the X-ray propagation. So this actually found very cool because it would mean that we could take these concepts that came from mathematical physics via optical photonics up to the X-ray realm. And we have actually tried to do this. So we have had beam time, and we are happily ever after evaluating the data that we got for spectra for different magnetic field values, simply to see that we have observed the experiment at this exceptional point. And it turned out, so the main problem here from the experimental side is that we are not getting directly just the energy spectra that we would need in order to extract then these eigenvalues. We are getting both time and energy spectra at the same time. These are 2D spectra with time and energy. And then out of these, you need to extract just the energy spectrum. And this was not that trivial. So we are actually right now, we've developed and improved the phase retrieval method to get out of those spectra the energy spectra that we need for proving, so to say, that we've seen exceptional point. So this is still work in progress at the moment, but we hope that will be done soon with this proof of principle, and then later on we can also go towards more applications of control using this PT concepts. Now, another idea that we are also at the point of evaluating experimental data. Now, these theorists doing experiments, this is very bad. But see, at the synchrotron, you can go and do experiments because there are teams there which can support you, and the whole infrastructure is there. So it's not like having your own lab. But every time you do an experiment, you realize that life is more complicated than you think as a theorist. So that's how it goes. Second idea that I would like to share with you would be that if you go for more than just 2 layers of resonant nuclei, one can work towards generating dark states in many layer structures. Namely, the idea would be to take these green layers. So the green and the red layers are all having the same nuclei in. I'm just depicting them in different colors because we are placing them at different positions in the cavity field. Namely, the 2 green ones are at the antinode, so they see plenty of light, and the red one is at the node and sees no light. Now, and this is where we are. It turns out there is a very interesting dynamics here in how photons are exchanged. So it turns out that the Hamiltonian that you can write looks exactly as an effective James Cummings cavity QED Hamiltonian, where you have a dark state and a bright state. A bright state would be the symmetric combination of excitation in the 2 green layers, and the dark state is the antisymmetric combination. And this antisymmetric combination feeds, so to say, or excites the nuclei which are in this layer, the red layer. And this brings us into a true, if you want, strong coupling regime, because in this Hamiltonian, you really can get a situation in which this field, the dark side field, is interacting strongly, so to say, with the nuclei in the red layer. And this idea is actually very much inspired by a paper by Oscar Peter and Derek Chang, where they were doing this in the optical regime with some nicely geometrically arranged qubits. And there they were looking for generational non-classical states of light. And it would be, of course, very cool if we would also be able to do this with X-rays. And also here we had the beam time, and we are evaluating data, as I told you. So this time it was an experiment at Spring 8. And we are also pretty confident that we have seen this effect. Okay, and the third wild idea that I wanted to introduce to you is very much related to the fact that I moved to Würzburg, and Würzburg has an excellence cluster, complexity and topology in quantum matter. And topology is for them very important. And our idea would be now that is there any possibility to exploit topological effects also in our cavities? For instance, trying to implement something like the Su-Schriefer-Hege model from topology. For the ones of you who are maybe not aware of much of it, it's something very simple, which started many years ago, back in 1979, when people were trying to investigate how solitons behave in acetylene. And acetylene is a long chain, a 1D chain of carbons, and they are coupling ones with a single bond and then with a double bond. The next one's with a single bond, the other one's with a double bond. So it's basically something like this chain here with carbon atoms there in place. And there is a different coupling between each neighbor. So A and B interacts with T, B and A interacts with coupling strength T prime. And you always interact only with your nearest neighbors, so to say. And this T and T prime have different values. And it turns out that if you have T smaller than T prime, then at the edges, there will be edge states emerging. And basically, if you send light through these chains, you can have excitations collecting at the lateral side of the sample. And this is something that we would like to do also with our thin film cavities. For instance, by constructing some geometric pillars. And if we go even further into that direction, we could try to do the so-called non-Hermitian skin effect, which is a kind of Su-Schriefer-Hege model where instead of the T prime that we had before, now we have some anisotropic coupling. So we have a coupling which, if you go from neighbor B to neighbor A, it's T minus delta. And if you go from neighbor B to neighbor A to neighbor B, then it's T plus delta. So, right, the two directions are no longer the same. And this is what we call anisotropic coupling. And if you do so, then one can obtain even more interesting topological effects, like topological funneling of light. And in our case, we'd like to do this with X-ray light. So these are also wild ideas that we are working on. Now, I think the main idea would be at the end that we can play, and we plan to play, and we do play at the moment with these nanostructures in all sorts, because we, from theory side, now have strong tools with which we can really treat them and design, so to say, check spectra and design structures for different possible setups and applications. So coming to the summary of what I told you, I hope I was able to convince you that it could be very interesting to have quantum control of X-rays for controlling the special X-ray propagation, or for getting, for instance, smaller sources that could come out of these topological effects, or for employing them for new material probing techniques. And the main question that remains for us, I would say, the outlook is whether we can exploit some non-Hermitian or topological aspects to improve this control for a number of various applications where X-rays, with their properties of penetration, of focusing, of short wavelength, for instance, also higher momentum that they carry with, could be very nice in quantum technology or for material science or even for biochemistry. So with this, I'd like to thank the people. My group in Würzburg had the interesting ideas of how the group photo should look like. You can guess what's the word that we try to depict here. And I thank all my collaborators, the funding that I have from the German Science Foundation, and also I thank you for your attention.
So thank you so much for a really nice talk. Other questions, comments? Do feel free to raise your hand or put your comments on the Q&A tab. Before we start, I would like to call your attention to the fact that this term, our Atto Fridays season, is really short because we are organizing the Quantum Battles in Atto Science 2023. And the registrations are already open. It's going to be at UCL from the 28th to the 30th of June. So do go to www.quantumbattles.com and register. I'm putting the link there, just 1 second. We're also going to have contributed talks. You can submit a contributed clip and do have a look. We have quite a lot of invited speakers already. We're putting this together. We forgot how much work it is to put together a real conference. So yeah.
Carla, this is hybrid, right? So
I mean, we don't know how much hybrid is going to be. Okay, to a certain extent, we know that before the battles, there's going to be a tutorial, and there's going to be these 3 panel discussions, which are the battles. They're going to be live streamed, definitely. Okay. Now we need to see, because we are kind of struggling, that we are trying to hire the professional streaming team from UCL so that we don't have to do this ourselves. We know how to do it, but we'll be busy with other stuff. And, you know, it's not a negotiation if everything is going to be hybrid. We're going to try to make it as hybrid as possible, but it's depending on a lot of circumstances. So it may be that there are things that happen on site that are going to be recorded, but not necessarily online later on. And it is, it's more expensive and more complicated than you think.
I know. We were 1 year ago organizing hybrid stuff. I think it's a nightmare. Absolutely. Yeah. So. Yeah,
I mean, I want to make it hybrid. Yeah, I want to make it hybrid because, and we all, not only I, because it's a team, but we are aware that also, you know, sometimes you cannot make everything hybrid. But for instance, if people want to submit a contributed clip to our YouTube channel, they are welcome to do so, or these kinds of things. And we have a comment. Javed Akram, excellent talk, really interested now on X-ray quantum optics theories. So I'm glad you are. Do you have anything else to ask? Because I see people are quiet, and I really liked the PT part that you're trying to look at when you had PT symmetry, and you were mentioning, okay, there may be some ways of obtaining that and using exceptional points, but I can see you still have some kind of decay.
Yes, that decay is very difficult to completely eradicate. Yeah, because so typically in this optical communities, they have gain and loss, so they kind of balance loss and gain together, and then they have the interesting effects. And there are some works which work on this kind of what they call quasi-PT, where they say there's still this merging of eigenstates. So the behavior is still there, but there's an overall loss on top. And in our case, it would be very difficult to counteract with this overall loss, because for us, it's difficult to get gain inside, right? I think it would not affect necessarily the physics, because the existence of exceptional point is there, but it would probably make the control effect a bit less spectacular, just by the fact that you do have all the time still some decay channel, which is not counteracted against.
Okay. I was wondering also, this is from Mark Ranavake, it's not from me. Feel free to raise your hand if you wish as well. We'll allow you to talk. But Mark is wondering if you have used excited isomers of thorium or cesium, and relying on forbidden decay transitions to achieve artificially high population inversion lifetimes to produce standard lasing only in gamma rays to achieve superradiance. So this question is more related to superradiance.
Yeah, it's okay. It's okay. I can try. So, the forbidden decay transition. So thorium, if you're talking about thorium-229, that's an M1 transition. I have not mentioned, it's the same here. So the iron transition is not an electric dipole, it's not an E1, it's a magnetic dipole transition. And nevertheless, everything works as I have depicted. So we are not achieving here high inversion levels, right? Because I told you most of the time we excite one nucleus. If we're going at the extra-free electron lasers, we have some calculations, and there are also a couple of experiments which have been performed, and you can excite more nuclei at the time, but you're still far from population inversion at the moment. So one would need to have probably really a seeded X-ray free electron laser, which has even narrower bandwidth for the pulse in order to really produce a high excitation for iron. About the cesium isomer, I cannot say, but for thorium I know, because that's 8 electron volt, right? That's in the range of VOV lasers, which are still yet to be designed and built. But I guess so. I think with thorium and also with iron, we do have a chance to obtain population inversion. Actually, we do have a work on some tapered waveguides where you can focus the light somehow in and obtain at one position population inversion. And afterwards, you can get lasing there. So I'm wondering now, so far I was not able to sell this very well in the respect that so if you have a narrowband laser to excite thorium and you obtain afterwards some lasing from thorium, you know, but you have already the laser on that frequency. So why is it much better? So I'm wondering what one would do with it. But I think it will be enriched soon. Yeah, it's not enriched today, but it will be enriched to have nuclear population inversion and to really obtain some, yeah, if you want a gamma ray laser, so a grazer. So this will be possible. Whether that laser would be very, you know, commercially interesting to do something with it, that I'm not sure. Okay. I hope this answers your question.
Yeah, is that okay? Or would you like to ask further?
Or do you want some other aspects? So just throw in another line and I'll tell you more.
Yeah, I mean, or raise your hand. We have allowed you to speak. No? No, it's fine. Okay, thank you. We're ending our transmission right now. We have some people watching on YouTube. So for those on YouTube, have a great weekend and thank you for joining us live. Take good care of yourselves. It's going to be short today. We may have something after Easter. We may not have something after Easter, but we're going to have a great tournament in June, end of June. So do check the quantum battles. Is going to be on site, maybe hybrid. We don't know how much of it is going to be hybrid. We'll try our best, but there are some negotiations at the moment which are going on. So thank you once more to Professor Pálwiąy for joining us and see you soon.
Thank you for the invitation.